Okay, I think it's good time to begin. Uh, Enough students are there. What we were doing in the next lecture, a small part is remaining in the introduction part, and then we will start the new topic. Uh, if there are any questions in the previous lecture, you can always ask. Otherwise, we'll start. We were here in the next lecture. Slides are visible, Bridget?
Yes, sir, it is visible.
Yes, sir.
Okay. Okay. So we were here in the next lecture. I've given you one demonstration that how operating system can provide you an illusion uh, of many CPUs. I've shown you this program running on a single CPU, and still you can get the illusion of many CPUs. And this particular concept or aspect is known as CPU virtualization, which is going to be the focus of the first part of our course. And we will start today the CPU virtualization thing. There's one more thing, which is a small thing which is remaining, uh, which is known as virtualizing the memory. So let's spend 15 minutes on that, and then we will start CPU virtualization as a next lecture. Now, we all know that the model of our RAM is very simple. The RAM or main memory you have in your machines nowadays is very simple. It's just an array of bytes. Now, if you want to read memory, you have to provide address to access data stored there. You want to write into memory, again, you have to provide address. Now, when a program is running, the memory is accessed all the time. And you might have seen in computer organization course, there are two instructions. Uh, Normally the load and store instruction to deal with the memory. If you want to store something in memory, you want to load something from memory to CPU, or you want to store something from CPU to memory, load and store instructions are there. And if you remember, the program also is there in main memory. So to fetch the instruction from memory to CPU, again, you have to provide the address, and that address is given by the program counter. So there is a register in CPU that is known as, there is a processor register known as program counter, and that program counter is fed with the next instruction to be executed, the address of next instruction to be executed. This thing you know. Now, there's an interesting thing which we are going to observe through this program. So I have written a very simple program just to give you an insight about how modern day processors and operating systems are dealing with memory. So in this program, I'm allocating memory size of integer by using malloc, and then I'm printing the address of that memory. You know that this is a pointer variable, and I'm printing the address of this memory. See the mouse pointer, and I want this address to be of 8-bit. That's why I have used these things. Then I'm using a system call getPID. More on this system call later. GetPID is a system call to know the process ID, whatever process is running. If you want to know the PID or process ID, so there is a system called getPID. More on this later. I'll be coming to onto this, the PID thing. Your address is always unsigned. That's why I've given unsigned here. Then what I'm doing, I'm initializing this uh, pointer with 0, and in a while loop, I'm just after sleep of 1 second, I'm incrementing the value of this pointer. So that's what is explained here. Allocate some memory. It prints out the address of the memory. Put number 0 in the first slot, the first allocated memory, and in a loop, after delay of 1 second, after sleep of 1 second, this value at memory is getting incremented. And with every print statement, we are printing that value and the ID of that process. This is what this program is doing. Now let's see uh, how we can run this program. When we run this program, nothing special is there. So memory address of P is getting printed, and then this process ID is coming. 2134 is a process ID, and initializing by 0, it is after every 1 second it is getting printed. So let me see whether we can run this program or not. So I hope my Linux box is visible to you. So I've already created the object file of this program. So let us run this program and you can see it. You can see this is happening after every 1 second. The process ID, first of all, the address is getting printed, the address of P, and then process ID with incremented value of P is getting printed. Now, let's do one more thing. Let's do one more thing. Uh, Suppose I run 2 instances of this program. Suppose I run 2 instances of this program. So what you are visualizing. So let me stop these two processes which are running. What are the IDs of these processes? 4439. Fine. So you can see here, and is there anybody who can answer this? There were two different programs, two different instances of the same program, but both are getting same memory addresses. Now here I want you to think over it. Both are running together. Both are running together, as we have seen in the previous example also, that CPU gives you this operating system gives you illusion of many CPUs. But what about memory? Both are running at starting from the same memory location. These are two different programs. Must be running at different memory locations. What is happening here? Can anybody answer this? Abhigyan, you got the problem?
Yes,
You
sir. Yes, sir.
understood the problem? So
Yes,
there
sir.
were two programs, both are have initialized the pointer. Now when I'm printing the memory addresses, they are giving you same memory addresses. Any answers for this? Anybody else who can answer? Suppose I ask Anshuman Bhargava.
So I don't.
You don't know? Any ideas? Aman Singh, any ideas?
Hello, sir.
The logical thing, they must be running in different memories because they are two separate executables.
So there may be means the thing may be like that. When one instance of a program is run, then when the one memory is getting free, then after the other one is running. So it may get
No,
allocated to.
how it is getting free? Because both are running together. You can see both are having while loop. They are not terminated. They have not finished.
But the order of in the order of printing, we can see that the instance of the second one is running just after the first one. So sir, there must be some very
So
small time difference.
there are two. So you mean to say that memory is getting overwritten? One program is writing memory, then another is overwriting it. It cannot
uh,
happen.
yes sir.
Now, this is what is the main concept of virtualizing the memory. And that's what we are going to see later on. Fine, that's what we are going to see later on. We can resume the slides. So that's what we have seen, that they are getting the same memory addresses. Now, each seems to be updating the value at the same memory address independently. And it is looking like as if every program, each running program is having its own private view of the memory. Now, how this is happening? Because operating system is virtualizing the memory. Now, it is not the main memory address you are actually seeing here. It is not the address of your RAM, your main memory, you are actually seeing here. It is a virtual memory. Each process, operating system provides each process same chunk of virtual memory, starting from some zero address to the highest address. Now, when you run a program, at the very last moment, the actual address binding is happening. Means both programs are having their own virtual address space. So the addresses you are visualizing, the addresses which are getting generated by CPU as program counter, the addresses you are visualizing here are virtual addresses. Really, in reality, they are not running in the same memory location in main memory. In main memory, they are running, when they are actually running, they have to be in physical memory, and in main memory, they are running at different places. But they are being allocated similar virtual address space. This is going to be our another focal point of our course. That how operating system maps this virtual address into physical memory of the machine. This is what we are going to see in our another module of operating system. So with this, our introduction is over. The powers of operating system I have already explained. The important issues like race condition, the synchronization, the CPU virtualization, and now the memory virtualization, you can see I've covered. And now it's good time to start our first lecture, or rather second lecture, which is CPU virtualization. Is there any doubt or question you want to ask? Brijend, any question here?
No, sir.
Okay.
हेलो सर.
Yeah.
सर ये बिल्कुल वैसा ही है कि सर जो हम लोग पिक्चर देख रहे हैं, मतलब सर जो दो दो सेम एड्रेस आ गए थे. सर मतलब ये बेसिकली ऐसा ही है जैसे सर रेस शुरू होने से पहले जब सारे स्टार्टिंग लाइंस पे सर मतलब खड़े रहते हैं लोग, तब की पिक्चर देख रहे हैं सर हम लोग.
नहीं, लेकिन रेस तो चल भी रही थी.
नहीं सर, चल भी रही थी, रेस बाद में स्टार्ट हुई ना सर. मतलब
रेस तो है ही नहीं, मेमोरी तो अलग अलग होनी है, क्योंकि बोथ आर राइटिंग. रेस condition is the situation when you have to write same memory location. Means two separate program wants to write on same memory location, or wants to read or write the same memory location. Suppose suppose I've given you example of race condition in the previous lecture. Suppose there is a linked list. There is one program, one process or one program wants to delete a node from the linked list. And another program wants to traverse the linked list and print the data items in every node. Now, if a program is deleting a node from the linked list, you know that there are various steps you need to perform. You need to move the pointers, then free the memory. And then, so while you are deleting the linked list remain in the inconsistent state until unless the deletion process is completed. Now you are not sure whether your program would be running for those many instructions. Your program may be coming out of the CPU. Let's say that, okay, 40% of the deletion work is done. It might have moved the pointer, but could not free the memory. There are some dangling pointers. 50% of the deletion work is done. And another process who wants to access the linked list and traverse the linked list get into CPU. Now this is race condition. Because now if another process wants to read the linked list, cannot read it because it is in inconsistent state. So that day I've discussed that, okay, if there is a race condition like this, then the process who wants to delete has to lock the linked list. And until unless the deletion process is completely over, the lock will not be opened. So if deletion process has started and locked the linked list, even if a reader process comes to traverse the linked list, it will not be able to unlock it because it has been locked by another process. And that day I have explained this thing. You got it, Ishan, now?
Yes, sir. Thank you, sir.
Okay. Okay. Today we are discussing something else. They have to write in different memory. They are two different programs. They have to be running, or they have to be stored in main memory at different places because they are two different executable. But still you are able to see, you are seeing as if they are running in same memory addresses. So what OS gives you? OS abstracts, OS hides the actual main memory and gives you a logical manifestation, which is virtual memory. OS says like this, okay, you have also got this virtual address space, you have also got this virtual, so everybody is having the same virtual address space from 0 to some highest memory. But when actual running is going to happen, actual execution is going to happen, at the very last moment, these virtual address spaces has to be translated into actual physical addresses. That is again done by your operating system. We will be seeing this in our one module, that is memory management unit. You might have seen this thing a little bit in your computer organization also, where you have studied virtual addresses and all that thing. Got the point?
Yes, sir.
Clear, Aman, now? Okay. So let's start the CPU virtualization lecture. And here we are going to see the process abstraction. This term I keep on telling, and you keep on hearing this term, the process. First of all, statutory warning. It is going to be a very heavy module. Fine. It is not going to be easy. So be very attentive. Lots of new terms are going to be there. Be very curious. Even if you are not able to understand any small point, just interrupt me. I will explain it again. I will not move ahead until unless that point is clear. And the most important thing, if the concepts explained in this lecture or this module are not clear, then forget about knowing operating system. Because this is the heart of the operating system, this lecture. So let's begin with understanding these two terms, program and process. Program itself is a lifeless thing. It just sits on your secondary memory. It's having a bunch of instruction, some static data, maybe, and it's waiting to spring into action. So when you write a program, it is just a lifeless thing. It's just a dormant thing which might be there in your hard disk. Now, operating system take these bytes and piece of codes and some static data maybe and make it running. The operating system transforms this program into something useful, and that something useful is known as a process. Now, process, it's an abstraction provided by operating system. And as we have seen in the previous lecture, that it provides you, it helps in providing illusion of many processing units. Simply saying, means in many books you may get this definition that process is a running program. But there is a small catch here. When we say running program, it does not mean it's always on CPU if it is running. A program might have started execution, but now if it is waiting for some IO to happen, then process might be out of CPU to give chance to another process, as we have seen in the multitasking and multi-programming example in the previous term. So when I say a running program, it does not mean that it is on the CPU all the time. Running means it might have started execution. Currently, it may be running or not running depending upon at which point that program is. If it is waiting for some IO to happen, it might not be on the CPU. But still we'll say it's a process because it had started execution. A process is a basic unit of execution for an operating system. This is the most fundamental job of an operating system, to convert a program into process and then run it on the CPU. So whether it's your program or operating system's own program or any other system program, program is a dormant thing, is a lifeless entity. Operating system converts that program into a runnable entity, into executable entity, and it is a most fundamental job of operating system to convert a program into process and run it on the CPU. Now, another thing which is very important, and you might have heard this or understood this in your computer organization, and that is interrupt. When you see operating system, a working operating system, it is almost always running some process. They can be application process, user process, or its own system or kernel process. The operating system also is a group of program, a bunch of program. So operating system might be running its own process or user process or application. Now, what is an interrupt? Interrupt is an event that, which is true to its name, that it interrupts the running of a process. And when an interrupt occurs, a lot of things has to happen. So let me switch to my whiteboard and let me explain you this thing. And then you will be clear why this abstraction is needed. And I have already raised this issue in the previous class. Suppose I am saying that there is a program, a small program main, and it is having many lines of code. Fine. And this program is running on your CPU. This program is running on your CPU. It's running on your CPU. Fine. Now, suppose there is a double click. Suppose you are already running this program, at the same time you double clicked any icon on your desktop. And let's assume for a while that there is only one CPU. So program is running, and then you have double clicked your mouse. So what is this? This is a mouse interrupt. A external stimuli is generated to CPU. Because when a mouse double click is there, you need to handle that. Now, if there is only one CPU, you cannot keep on running this program. Because now what you need to do, you need to handle this event. You need to handle this event. So suppose at line number 1005, when the program was executing line number 1005, this interrupt, mouse interrupt came. So obviously this program, suppose we say this program P1 has to leave the CPU. Now CPU somehow has to have knowledge and you might have studied in your computer organization that there is interrupt priority decoder, interrupt decoder, and then interrupt handler, interrupt vector routines. Means to handle the interrupt, there has to be a interrupt handler code. So this program P1 has to leave the CPU, and then this interrupt handler code to handle the mouse interrupt has to come inside the CPU. This interrupt handler code will run to handle this mouse interrupt. And afterwards, another thing means because you have double clicked some icon, you have to open that program to execute. Whatever you have double click, you have to open that program to execute. Means you need to copy the program code from the hard disk to the CPU to run the program which you have double clicked. But first of all, you need to handle the interrupt. Now suppose this is the situation. Now this is interesting. So once the interrupt is handled, and suppose you have run this program which you have double clicked, later on P1 which was interrupted will get a chance to execute. Now anybody can tell me from which instruction this program will execute when it gets a chance again. Aman? Aman, Abhigyan, anybody can tell?
So from where it left, sir, the last time.
from where it left. But where is this information? So program was executing 1005, has completed its instruction cycle. The next instruction was 1006, suppose. Fine. Next instruction was 1006. So where is this 1006? Because now you have to execute P1 from 1006. And what are these 1005 and 1006? Yes, Abhigyan or Raman.
Sir, the interrupt handler code will store this, I think.
Now, first of all, these 1005, 1006 are program counter. You know that? So there are three cycles, as you know, in computer organization, that there is fetch, decode, execute. These are the three basic cycles. When you fetch an instruction from memory, when instruction is fetched, at the same time PC is incremented to point to the next instruction of the code. And then instruction is decoded, and then finally it is executed. So your PC plus 1 is stored in a register known as program counter register. But once you have left the CPU, the interrupt handler code has arrived. So interrupt handler code will load its own program counter. The program counter register will be loaded by the memory address of interrupt handler code. Yes or no, Abhigyan?
Yes, sir.
So what about this?
Sir,
So this,
maybe
yes. Yeah,
sir
carry on.
stack में store करता हो sir.
Yeah, we'll see that. We'll see that how this is happening. But first of all, I just wanted you to see the spirit of the problem. Now this is happening. This is happening. Operating system keeps on doing this thing. A process will start execution, another process will come. So the old process has to leave, new process has to execute, new will go, another will come, and interrupts keep on happening. Now, what is going to happen when an interrupt occur? OS has to save the context of the current process. I have given you only one small part of context, that is program counter. There are many other things, many register. You know, there are general purpose register when a program is executing, when a code is executing. There are many things which are happening. Many registers are having the values of that program. The stack, system stack is having every stack pointer register, this register, that register, as you have seen in computer organization course. So when a program runs, it creates a context on the CPU or on processor. It uses the processor register, program counter register in its own manner. Now what you need to do is, when that program leaves and still execution is remaining, you have to take a snapshot of that CPU. That when I was running, when that program P1 was running, what is the situation there on the CPU? That snapshot of that CPU has to be saved, so that next time when this P1 process gets chance, it can start as if it was always running. And that's how you can provide an illusion that there are many number of CPUs. When you don't get an idea whether the program has stopped execution and then started execution, you think that both are executing at the same time. You know that you need to save the context. You need to save the context operating system will help you in saving the context. And what is the context? Consisting of some information like program counter and other register so that it can resume the process where it left off. And then obviously program counter will point to the code of interrupt handler and executes that code to handle that interrupt. So this will keep on happening, processes and interrupts. And that interrupt will actually gets handled and may give chance to another process for execution. And that's what is there in this slide, that after servicing the interrupt, OS goes back to executing processes again, either the same process that was running before or some another process. And before running a process, you need to reload the context of the process which was saved earlier. So if you see, any typical operating system is a event-driven architecture. Some event will happen, OS will handle the event. Again, an event will happen, it will handle the event. And meanwhile, it keeps on giving environment to execute the process. Let me see if anybody is asking any question. Yeah, some question is there. No, there is no question. Okay. Somebody is asking something? Okay. Anyway, so now let's see process from the memory point of view. Here, this is a typical layout of memory of any process. I don't know whether you have seen this in your computer organization course or not. So if we see memory layout of any process, what it is going to have? It is going to have text, means see the mouse pointer, means your program code. Some static data, like your static variables in C, some constant arrays and strings and constant variables. Dynamic data, which are maintained in a heap data structure, like your malloc in C, new in Java, and all that. So heap grows from lower memory address to higher memory address. And then stack. This stack is used for saving registers when you make a subroutine call, function call. And this stack and heap grows towards each other. So this is a memory layout of any process. And then there is one area which is reserved. I'll come back to this in a while. So this is the memory layout of any process, typical memory layout of any process. When a process runs, program counter of the CPU points to some address in the memory image of the process. Here, program counter will reference the code of the process. And where is the code of the process? In the memory image of the process. To read code and write data. And as I told you 15 minutes earlier, that CPU does not need to know the actual physical addresses in the memory. Every process has a virtual memory address space starting from 0 to the maximum value. That maximum value depends upon the architecture of the system. And actually, it is dependent upon the number of bits to store memory addresses in your CPU register. To store both virtual address and means to translate from virtual address to actual physical address, you need to register, virtual address register and physical address register. So what would be the maximum size of virtual address? It depends upon that what is the size of that virtual address register where it is going to be stored in CPU. Fine. But a major point here is that every process has a virtual memory address starting from 0 to the maximum value. That depends upon these two things. And I have shown you, demonstrated this also. We have run two processes in one example, and we have seen that they are running as if running in a same memory space. They are not running in the same memory space. They are running in their own virtual address space, which is similar for every process. Now, for example, a virtual address space of a 32-bit machine would be from 0 to 4 GB. Means every process can use this 0 to 4 GB virtual address space. Now here at this particular point, I need to again switch to my whiteboard and let's see whether we can understand some important point. Now, Aman, what is compiler?
Sir, when we write a code, then we used to firstly run out compiler to check the correctness like that.
What actually does compiler?
Sir, it actually means convert.
Converts what?
The language we write into the machine language that computer may understand.
Simple, high level to
Low level.
high to
Low.
machine level.
Yeah.
Okay. So means your C to machine code. Okay.
Yes.
Now I'm writing a assembly language code, a small assembly language code. And you might have seen the code like this. Suppose I'm saying move A, B, add A, B, whatever. Means I'm just writing a random code. Subtract B, C, fine. Then jump. Have you ever seen this jump instruction anywhere in assembly language code?
Yes, sir.
Jump to where? Or if I want to call another function or another subroutine. So when I say jump, jump to where, Abhigyan?
Sir, that instruction number, that
Which? Anywhere in this
like,
code, no?
yes, sir. So we have to write which.
Above. So you generally write in assembly language this label, no?
Yes.
And then you suppose I want to jump to some label P. So you write in assembly language that P. Okay? So just to easiness, okay, you jump to P from here. Okay? But it does not happen like this. Actually, this label P, and now every line is having address also. Say 1005, 1006, 1007, and so on. So when I want to jump here, suppose this line is 1009, I want to jump to here, I would provide this address 1009. So jump to 1009. Now, when compiler converts your high level language code to machine code, compiler wants these addresses also. Yes or no? बच्चा लोग?
Yes, sir.
Rajendra?
Sir.
Compiler need these addresses. Okay? But you are compiling only. You are just writing GCC. Okay? So where are these addresses? What are, means you haven't run the program. You don't know which portion of main memory your program is going to run. So what are these addresses? Yes, Brijendra.
Yes, sir. It is virtual addresses.
Now you know the use of virtual address.
Yes.
You require some address space at the time of compilation.
Yes, sir. It is necessary. Otherwise, it
You
won't be
are not
possible to
able to
compile.
provide addresses. Because actually where this program is going to be stored in main memory is needed when it is running. And we have seen this at the time of running also we were getting virtual addresses. At the actual last moment, the actual addresses are going to be decided, but we need some. Now, another problem is, suppose I say, you can compile a code somewhere else and run executable on some another machine. Yes or no, Viren?
Sir, yes, sir.
Obviously, we can do that thing.
Yes.
Code is compiled. When you install any program, those are executables, no?
Yes, sir.
Those might have compiled somewhere else. Now, program is getting compiled somewhere else and it is going to run somewhere else on another machine. How can program get the actual addresses?
Yes, sir.
I think now this point is clear to everybody. Abhigyan?
Yes, sir.
Is it okay now?
Yes, sir.
Okay. And that's what I wanted to explain. Now let's move to our slide. And that's what is written here in the slide. Virtual addresses are assigned to code and data by the compiler in this range. And for every process, the range is going to be same, 0 to 4 GB if it is on 32-bit machine. And that day in lab, you have seen one thing, 32-bit machine, 64-bit machine. So when you install any program, you need to tell whether you are going to install it on a 32-bit version or a 64-bit version. Operating system is also a program. So operating system for 32-bit machine is going to be different from operating system for 64-bit machine. CPU generates and requests code data at these virtual addresses at runtime. Even the CPU, when requests for code or data, will generate the virtual addresses. Now, these virtual addresses which are requested by CPU are converted to actual physical address at the very last moment before the addresses are seen by the physical memory. So at the time of compilation, you provide addresses in this range, 0 to 4 GB. This is example for 32-bit machine. When CPU runs the program, it requests virtual addresses. At the time of very last time, these virtual addresses are converted into actual physical addresses. And then your program is executed. This is what I wanted to highlight. So how it is getting done? Operating system maintains these address translation maps. We'll see these things in detail later on. Some of these things you might have seen in your computer organization like paging and segmentation and all, but we'll be seeing in a different manner in our course. So these address translation map are used to translate virtual address to physical address. It is done with the support of a piece of specialized hardware called memory management unit. So the CPU architecture is having a hardware known as memory management unit. And with the help of operating system and memory management unit, these virtual addresses are converted to physical addresses or actual main memory addresses. Now this assists in separation of these addresses also, virtual address and physical address. Now every program can be very big. So you are not bothered whether your system is having 2 GB memory or 4 GB memory. You can write your program as big as possible. Each process can logically number its address space starting from 0 to some maximum limit. Any questions at this point of time? Any questions from anybody?
Excuse me, sir, I had one doubt.
Yeah.
So basically, when we compile and run the C program, we can divide in two stages. First compilation, then running its executable file, right?
Yeah. Yeah.
So when we compile it, so there is some instance and we use the memory, right?
Let me explain it again. When you compile, as I have shown, you don't know where this program is going to run. You cannot know the actual addresses. Fine. So you require some addresses. Some address space is needed. And that address space I'm terming as virtual address space, which is same for every process or program. Now your program is compiled with these addresses. Executable is created. exe.exe is created. Still, this executable is having these virtual addresses. Now what will happen? CPU loads program counter, and when this exe is created, the memory image of process is created, which is having text section, as I told you, fine, and static section, heap and stack. Now when CPU generates an address, CPU will generate an address in this text section, and this is going to be virtual address. And that's why when we seen that program, the pointer P, whatever address we were seeing in that program ./mem, we were getting the virtual address. Fine. So CPU generates virtual address, but you don't know where this program is actually located. This program might not be in main memory. तुमने डबल क्लिक किया, suppose you have double click MS Word icon, MS Word is residing in hard disk. So when MS Word start execution, CPU will generate virtual address of MS Word program, MS Word executable. Now what this MS Word is not even in the main memory. Now later on we'll see this virtual address has two translation. Virtual address can be translated into where in hard disk, and then virtual address can be translated where in main memory. So you'll keep this translation to know from hard disk which sector of hard disk, which cylinder of hard disk I have to bring MS Word code to which location of main memory. And both are getting done by operating system, because CPU does not know about where in main memory. This is happening at very last moment. Now you got the point?
Yes, sir.
Okay now?
Sir, but when we are compiling, then compiler is a program, right?
Yeah.
So does that mean that it is not interacting with the physical memory at all? It's working on a virtual memory.
Compiler is executing, no? And that's why it can, compiler is a program. So compiler executes, compiler is running, executing. The input to compiler is a program, which is your high level language. Fine. Output of that compiler program is your machine language level language. So when compiler gets the input as C program, suppose C program compiler GCC is there. So what you provide as an input to GCC, your own C code, 1.c, 2.c, okay? So that input program will go, and then the output program, and in high level language, you don't give memory addresses to the statement. You just write in high level language. So this program will go inside, compiler is executing. First of all, compiler executes, GCC is executing. It is taking your input program, and then it is creating a machine level language code. Fine. Machine language program, and there we need addresses. So compiler need to know which addresses I have to give this machine language code.
Oh,
And
okay.
that's what I have explained here. So this is your machine language. I have written in assembly. Finally, this move would be having machine code. So these are the machine level language code. Jump would be having its own respective machine level language code. Jump with address. So these addresses compiler needs to know. These are not actual addresses. Yes. Any other doubt?
मयंक,
Yeah.
ये लिंकर लोडर भी कुछ बताएगा क्या इसमें?
नहीं 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 अभी अभी
छोड़ा
नहीं
छोड़ा,
नहीं
ठीक है,
कंफ्यूज हो जाएंगे सर
ठीक 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 ठीक।
अभी नहीं बताऊंगा वो बाद में सर एक्चुअली दैट हैज टू बी डन इन कंप्यूटर ऑर्गेनाइजेशन
ठीक है, ठीक ठीक ठीक
लिंक लोडर
ठीक।
and then I need to tell them the address binding concepts, compile time, run time, load time, and all that. Right now, it's not needed. Any other questions? Okay. Okay, fine. So let's move ahead. Now, this is going to be very interesting. Fine. And please, if you are sleeping, wake up. This is going to be important, very important. Please pay attention. Let's revisit our first lecture code. I have given you one small code, main hello world. And I have asked you a question that do we need an operating system intervention? And then we discussed this, that yeah, operating system intervention is needed because at a user level, you just use printf, and printf is a function which is defined in stdio.h. But what printf is going to do? Printf is going to, means what you want this hello world to be printed on your monitor. So as you know, there is a standard output file. So in printf code, you need to open that file and write this hello word in standard output file, and then that standard output file will be transferred to the monitor. We have discussed this thing. Now there are layers of abstraction which is provided to you. I told you that day. For your own happiness and easiness, this printf statement is provided by your C library, studio.h. So you are not bothered about standard output file kahan pe hai, where is standard output file, how to open that standard output file, how to write into that file. You just use this printf. But at the end of the day, you have to if you see the printf code in this header file, you will see that that file is getting opened. Now you'll ask me a question that, sir, we have done input output in C also, where we can use fopen, fclose, and all those commands. That is again an abstraction which is provided by language to you. So when you do fopen, fclose, those are again functions defined in standard input output file. But how that file, which is a system file, standard output and standard input, these are system files. How these files are going to be written, those can only be written by operating system. So everything is abstracted from you by the language library. So language, C language provided you a library. You use printf. When you want to take input, you use scanf. When you deal with files, suppose you want to deal with files, you use fopen, fclose, fwrite. Fine. And everything is hidden from you. Everything is abstracted from you. But actually, operating system will come into picture, because that file has to be written, and then finally that file has to be the content of that file has to go to the monitor. And you haven't written any code for that. So operating system code will be invoked, and operating system comes in picture. So this printf will make a call to the operating system, and this is known as system call. And actually it will use an open system call to open the standard output file for writing. Now the problem here is, you know that OS is a program. Please pay attention. You know that OS is a program, and it has to run to manage other programs, as we have seen here. Running my hello world code, OS has to execute. OS has to execute because this printf will make a call to the operating system, and OS has to execute. OS executes to manage other programs. We have seen OS as a resource manager, OS as a um, abstraction provider, OS is virtualizing agent. We have seen all these things in previous lecture. Now the question is, if there is a single processor, for assuming for a moment, and I am saying that you know that operating system has to run to manage another program. Now if OS is running, how a user program is running? And if a user program or application is running, how OS can run and control and manage? That's a holy grail. Fine. So if OS is running, user program cannot run, assuming single processor. And I always take this example because we have studied operating system when there were single processors. And still at that point of time also OS was running on the same single processor. OS runs, user code run, OS run, user code run, and how this is happening, that's a question. This is what is the complete picture. And sometimes we say operating system as kernel. Kernel is the most important part of operating system. So we have seen that user process, simple user process like this also need OS. So kernel is somewhere in memory. So there would be some user processes or applications. They need operating system. There may be some operating system own process. They also need operating system. There are some devices, peripherals, monitor, keyboard, hard disk, they also need operating system. So how this OS runs? This is a interesting question. And that's what we are going to see in next 15 minutes. When a user program needs help of operating system, required to run some code of operating system executable. Means a simple user program like printf hello needs help of operating system code to actually print the things to the monitor. So requires to run some code of operating system executable. OS does not run as a separate process unless it wants to run a system process. So when OS runs its own process, then OS is running separately. Otherwise, OS always runs on behalf of another process. Now, please be very careful. I'm again repeating. More often than not, your user processes or IO devices require operating system. And in these situations, OS does not run by itself. OS runs on the behalf of another processes until unless it is executing its own system processes. Now, how this is done? The code of operating system, of operating system, normally we keep the kernel of operating system in main memory all the time. So most important portion of operating system would be in main memory all the time. And what we do, the code is mapped into the virtual address space of every process. Now this is right time to see this reserved. So every process is having a virtual address space of 0 to 4 GB. And some higher address space, higher address area of every process's virtual address space is reserved for operating system. And here, when you translate these virtual addresses to physical addresses, these portion of virtual addresses, when they are translated to physical address, they will always map to the code of OS present in main memory. This is the arrangement. This reserved virtual address space always translates to physical memory where OS executable is actually present. Now things are very simple. How to invoke the code of operating system? Just move your program counter to this area. And now you are dealing with the operating system code. But you are not required to do these things, changing program count and everything by yourself. For that purpose, we have a system call interface. There is another set of libraries which is provided by operating system, and that is system call interface. So whenever you want to take help of operating system, application or user process will make a system call. Making a system call means your program counter is getting changed so that it can refer to the reserved address space, virtual address space, and this virtual address space, reserved virtual address space, will always map to the actual code of OS, which is wherever it is loaded in main memory, it will always map to that particular position. So to invoke the code of operating system, just need to set the program counter to this reserved virtual address space. Any questions here? Any doubts? Brijendra,
No, sir.
got it?
No, sir. No, sir. Yes, sir. Got it.
Aman, Divyanshu,
Yes, sir.
any doubts?
No, sir.
Okay. Divyanshu Upadhyay, Abhigyan,
No, sir.
clear?
Yes, sir.
Okay. So let's move ahead. Now the popular confusion. Are there many copies of OS code in main memory? One for each process? Anybody can answer? Yes, there will be many copies of operating system code in main memory. Suppose there are 20 processes which are running, they might use operating system in any point of time. So there will be 20 copies of OS kernel in main memory so that they can map. क्यों अमन?
No, sir.
क्यों? Yes, Brijendra.
No, sir, it does not have. It is actually having the mapping just. ये वाला कोड यहाँ है, ये वाला कोड यहाँ है, ये
That's a
वाला
point.
कोड यहाँ है.
That's a point. That's a point. So we have only one copy of operating system in main memory, and this is how, by using an intelligent jugaad, this intelligent jugaad, we can share the operating system code among many processes. Because every process would be having a reserved address, virtual address space. And then we have made it a point that the reserved virtual address space of every process is going to map into the actual main memory copy of operating system. So in this way, many processes can share the operating system code by having only one physical copy in memory. And actually, it is not a new idea. This methodology is also utilized by many, other programming techniques. Like you make shared libraries or other large pieces of code which you want to share among many processes. So you need to just map the library into the virtual address space of every process which is required to use it. A similar technique we have used here, that your actual OS copy in physical memory is mapped to the virtual address space of every process, and every process is having a reserved virtual address area. In this way, the operating system code is shared among many processes. Now, but the important issue here is something else. Kernel getting mapped to the address space of every process is a security issue. A malicious user may try to modify the kernel data structure, because now you are able to go into the code of kernel. And if you are a malicious user or a virus or a program, you can do all those kind of things. So what has been done? Suppose this program is executing, simple program. So it is executing this line int main, it is character string hello world. Then it starts executing printf code in stereo.h. As and when there is a need of OS code, obviously you switch your virtual address program counter to this area, reserved area. Now what you are actually doing, you are executing the kernel code in a user program. So this has to be safeguarded. So there has to be different privilege level. Not everything of kernel code can be accessible to the user programs. And even if it is executing the accessible part of operating system, you need to change the mode of the execution. Access to the kernel portion of the memory of the process is restricted. User cannot access this area. User process cannot access this area. It can just provide an indication. I need a system call. I need to call the system. I need to run a OS routine. By system call interface, it can just make a call. And as and when a code of kernel is going to execute, operating system takes control. As and when code of OS is going to execute, now the master is operating system. Means what is happening? OS is executing on the behalf of the user process, but having rights with itself. And that's why there are two modes of privilege level. When a user code is executing, it is known as user mode. When kernel code is executing, it is known as kernel mode. And when kernel mode is there, only operating system can play with the things, not the user code. And in this way, the kernel code is protected from any malicious user or any, it may not be malicious user, you might do some errors in calling the things and you may disturb the kernel data structures. And that's why these two modes are there. There is a special bit in CPU. Right now, CPU is executing what? Fine. Right now, CPU is executing what? Whether it is executing the kernel code or the user code. What this assists in? This assists in forcing privilege instruction to be executed in kernel mode only. Kernel mode means OS is having power. So whenever you make a system call, whenever you want to execute the code of operating system, CPU will change its mode by setting a bit that is known as kernel mode bit. That no, right now kernel code is getting executed. It's highest priority code and nobody can disturb it. Nobody, only operating system is having privilege over this part of code. Even if operating system is executing on the behalf of user process cannot play with the things. अब अगला problem. In the memory image of the process, there is a stack, as we have seen. In memory image of a process, there is a stack. And stack is used to store the return address, to store another stuff when you are making a function call. But when you have started executing the code of operating system, means this user process has started executing the code of operating system code is executing. Operating system also needs to call function, its own function. So same thing, that's also a program which is getting executed. So for your program and function calling, there is a stack. For operating system program and function calling, we also need a stack, and that is known as kernel stack. When process executes in kernel mode, kernel stack is used. Means some part of the kernel address space of process is reserved for the kernel. उस reserved space में से, which is reserved for the operating system virtual address, some part of that reserved space is reserved for the kernel stack. So whenever you are executing kernel code, kernel stack is going to be used. Whenever you are using user code, user stack means stack in the user area of process is going to execute. It's going to be used. Kernel stack is also used, we'll see later on, to store the temporary state of process while doing transition from user mode to kernel mode. Fine. When you are moving from user mode to kernel mode, some user some state of whenever it was when it was executing in user mode, some temporary state need to be stored. We'll see that later on. When to switch to kernel mode? Interrupts. Whenever a peripheral device, you can see here in this figure, a peripheral device, keyboard, mouse can only execute by interrupts. So when you interrupt the existing process, you actually are trying to switch to kernel mode, because now operating system has to come into picture. It has to save the context of previously running process, start executing the interrupt handler. Who will do that? OS will. So OS takes control. As and when there is an interrupt from peripheral device, OS takes control. Traps, there are some exceptions from within a program. Traps are like interrupts, but they are not caused by external events, like divide by zero and all. Then again, you need to handle them. You don't have code for that. OS will come into picture. OS needs to execute. So kernel mode switching is done. And obviously, we have seen the system call. It is just like when you require OS routine to be executed, you require OS routine to be executed, like in printf, you require operating system to be executed. On behalf of user process, you make a system call. They are like system call that invoke portion of kernel code. They are also handled much like interrupt, because interrupt is also kernel code. Interrupt handler is a kernel code or OS code. And sometimes we also know as software interrupts. System call are also known as software interrupts. So there are 3 times when you need to switch from user mode to kernel mode when there are interrupts. These are external entity. Traps, some exceptions, some problems from within your program. System call when you have to make a call to the operating system. So in this situation, the program will switch from user mode to kernel mode. And all these events need saving the context. We'll see these things a bit later. Okay. Any questions you want to ask?
So please explain traps one again.
Traps are like, suppose you divide by 0. So what will happen?
Yes, a mathematical error means runtime error will be there.
Runtime error. Or there are another thing. Suppose you are playing with pointers, fine?
Yeah,
And
segmentation
you
fault.
did some error, and your pointer is actually addressing to another process area. It's creating some trouble. It's a trap, fine?
Yes,
So
sir.
traps are the stimuli, interrupts which are getting generated from within your program.
Okay, sir.
Peripheral interrupts are from external. It's not generated by the user code. It's some external entity is interrupting your execution. When from within the program, from the interrupt occurs, it's a trap. Okay? And system call,
Yes,
you
sir.
know. Got the point?
Yes, sir.
Okay. Now, there may be many process states. I'm not telling here you about the Linux process state or Windows process state or Unix process state. I'm here telling you about some general process state which may be utilized in our operating system, which we are going to take as a demonstrative example in this course, the XV6 operating system. So these are not the exact name of the process state of XV6, but very much similar. So basically, there can be 5 states. New, when a process is being created, it's a state. Process ऐसे ही नहीं create हो जाता है. There are lots of steps to create a process. अभी थोड़ा little bit you might be getting. You need to create the process address space, the memory image, then context, how to save the context, where to do these things, all these things. So a new process, when it is being created, is a state. Running, when actually it is executing on CPU. Blocked or waiting. This process is blocked on some event. It's waiting for IO or any other event. It is ready. It is not blocked or waiting for anything to happen. But because any other process is currently executing, so it is ready but waiting to be scheduled on the CPU. Terminated. when process dies or process finishes gracefully. When process has exited or finished, again it's in a state because it is waiting to be reaped by, or the remnant need to be transferred back to the parent. What is parent and what is child will be coming just now. So there are 5 states. State of the process, in which state currently the process is, and the context of the process is stored in a kernel data structure. It is a kernel data structure, but it is a part of your process. Maybe a user process or a system process, a kernel data structure which is a part of your process. So this is a data structure. It's interesting thing. This is interesting. Let me show you the process image again. So the PCB, process control block, is a data structure maintained by kernel, but it's a part of process address space. So state of the process and other details of the process are stored in kernel data structure known as process control block. And it is called task struct in Linux. So whenever you create a new process, kernel has to allocate a process control block for this process. And whenever process is terminated, this PCB or process control block of that process is cleaned up, it's flushed. So at the time of generating a new process, creating a new process, PCB is created by kernel. At the time of exiting the process, the PCB is flushed off. What are the contents of PCB? Now, the PCB contains process identifier. What is that? It's a unique identification across the system. Every process would be uniquely identified by this process identifier. Identifier and pointers to its parent and child process. What are parent and child? I'm just coming. The current state of the process, whether it's running, blocked, or whatever. A pointer to the kernel stack of a process for execution in kernel mode. Kernel stack है कहाँ? जैसे like there is a stack pointer, there is a pointer to the kernel stack of process for execution in kernel mode. Pointers to some data structure or kernel stack like process context, program counter, other CPU register needed when the context must be saved. So I was telling you, when you need to save the context, you need to take a snapshot of the CPU. So all the CPU register, program counter, and other register will be saved on kernel stack when the context is changed. More on this later. Information related to scheduling the process. What is the priority of the process and something like that. Information related to memory management of the process. Information about how many files a process has opened during its execution. File descriptors and other things. These are new jargons for you. And many more, much more information is there in the process control block. We'll slowly and gradually know about these information points. Now, the actual thing, how to create a process. So before doing this, I just need to ask something from, say, Divyansh. Divyansh,
Yes, sir.
main is a function.
Yes, sir.
Who calls main?
Uh, I mean OS.
Who calls main? Okay. So let me show you my Linux box for a while. So So if I am saying ls, what has happened, Divyansh?
So you have given a command, and according to that command, the program runs, just stored in the system.
So ls is a piece of code, no?
Yes, sir. It's a
A
bash script.
program.
A bash script. It's a bash script stored as a LS.
So now it has to run,
Yes, sir.
but a program cannot run. Program has to be converted into process first of all. I told you.
Yes, sir.
So who created this process? You got my question now?
Yes, I got it.
Now for that sake, anything. So I'm just on a terminal. So what is this? This is shell, no? You know that? You've done shell programming.
Yes, sir.
So I'm in a shell, and shell is a command line interpreter. I'm writing a command. A command is nothing but a piece of code that has to be executed. But before execution, this piece of code, I told you that's a dormant thing. It's a lifeless thing. It has to be converted into something useful. That is process. So who is doing? Who is creating process?
That's a OS creating the process.
No. That's the major thing here we need to know. In Linux realm, Linux, Unix, and another OS also, Solaris and all, a process cannot be created by itself. There has to be a parent process who can create a child process. So when we were seeing this, so a process has to be created to run ls, but process cannot be created by itself. There has to be some parent process to create a child process. So before ls, there has to be some parent process which can create a child process. And OS use this function, fork function, to create a process. So this is a system call, this is a piece of code of OS, operating system, known as fork, to create a new process. But who will issue this fork? Who will call this fork? A parent process has to call a fork to create a child process. And when a child process gets created, then ls can run. Are you getting my point or not, Divyansh?
Yes, sir.
So there has to be some parent which can use OS routine, this fork system call or fork function to create a new process. So there are three system calls to create a clone of parent process. We'll see what is a clone thing here. There are fork, wait, and exit. These are OS codes which are accessible to us via system call interface, fork, wait, and exit. And if you want to change the code of the process, then there is a system call known as exec. So there are four basic system calls to do these things. So we'll see each system call from on an abstraction level first at the system call abstraction. And then later on, we'll see that how this fork code is written in XV6 operating system. And then we'll play with that. So what is the mechanism? Parent calls fork. Child is created. This child is going to be exact replica of parent. And this parent and child will execute concurrently. So there has to be a parent which will do fork, a child will be created, and this parent and child will be executing concurrently. After fork, both child and parent keep running. That child may fork another. that another child may fork another, and in this way A forks B and C, B forks D, E and F, C forks G, D forks D, and in this way many process keeps on getting created. And it results in a process tree. Now who is the Brahma? Who is the ultimate creator? Where is the Big Bang thing? So root of this tree is init process. This init is created by operating system during system startup. And all other processes which are getting created during the course of operating system booting and running your programs and doing all those things are descendant of this init. So init is the first process which is created by itself, say Brahma, fine, which is created by operating system at the time of system startup. And rest other process, so init will fork something else, that something else will fork something else. In this way, all the process will be created. We'll come back to wait in a moment. So what is fork system called? Current process will split into processes. Parent and child. So parent will issue a fork, a replica is created, and now both parent and child are there in the execution. They can run concurrently. Now what are the return values? So when you call fork returns. It returns negative -1 if fork cannot create a process. If fork is unsuccessful. It returns 0 in child and process ID of child process in parent. So when fork is successful, fork is executed successfully, fork system call is executed successfully, it returns 2 values. 0 towards child and child process ID towards parent. Don't worry. Let me show you the next slide. Child process inherits identical copy of memory, CPU register, all files opened by parent. Means it's exact replica of the parent process. Execution proceeds concurrently with the instruction following the fork system call. अब वो exact replica है तो वही code उसमें भी आ गया child में भी. And in both child and parent, because PCB is also shared, PCB is also because whole memory image is exact replica, so PCB is also same. If PCB is same, PCB is having the CPU register, program counter, everything, program counter is also same. So after the execution of fork in both processes, next instruction will be just after the fork instruction. So execution proceeds concurrently with the instruction following the fork system call. So how fork works? So let us see this code. It's a very simple code. This is a parent process. Please be with me. This parent process is issuing a fork. Depending upon the return value of fork, it's a switch case statement. If it is -1, switch return, depending on the return value of fork. If it is -1, it's an error and exit. This is the parent process, code of the parent process. If it is 0, then say you can print I'm child. If it is default means if something else, then you can print I'm parent. So this is one program, a parent process. When you run this program, a parent process will be created. This parent process will be having text area. Text area means your code, data stack, and program process control block. This process may be having some resources, some file, and say PID of this parent process is 25. This is the parent. So in this parent process, as and when there is a system call, means you are calling fork, the control, the program counter will be changed, and now you start executing the operating system code. So your program counter will be changed to execute the code of operating system. Means program counter will be changed to refer to the reserved virtual memory address space of your process. This is the first step. Making a fork call, control is shifted to the operating system. Now operating system executes fork, and fork execution is over. As and when fork execution is over, another process will be created. PCB is going to be same, code is going to be same, data stack, everything is going to be same. Resources, whatever parent is sharing, and file, whatever parent is sharing, this child will also share, exact replica. But yeah, this would be given a different process ID because it's a different process. Now, this fork code which was executing at last will return. If it returns 0, means 0 is going to be written in the child process. The child PID will be written into the parent process. So just imagine a single code was there. This code calls fork. Another process is created. Now both can run. But this fork code actually returns 0 in the child process and ID of the child process to the parent. This is the arrangement. Both are sharing everything, PCB and everything. PCB contains the program counter. So both will be having same program counter value. So in both processes, whether it is child or parent, suppose child gets chance to execute, what is the next instruction will be executed? Switch statement. In parent also the switch statement, because when parent was executing this line, program counter was incremented to the next instruction. And when the fork executes, a new process is created with the same PCB content. So both will be sharing the same program counter value also. So both will start execution from the switch statement. Now see. But there would be a difference. When child executes, case 0 will be executed. When parent executes, default case will be executed. That is due to the switch statement, the return value. यहाँ पे return value 0 है, and here the return value is ID of the child. So default will be executed. So you can write a small program like this, and in different cases you can just put up printf statement that I am a child, I am a parent, and you can see how fork is working. Now next is important. In parent process, we have to have this another system call that is known as wait. Now what was happening? Suppose parent get a chance to execute. Parent executed this default case, and now parent wants to execute this wait. As and when this wait is called, control is again shifted to operating system. Now this operating system wait code is nothing but this wait code is forcing parent to be blocked. तो पेरेंट चलेगा, अपना पोर्शन एग्जीक्यूट करेगा, will call wait, control will be shifted to operating system, and now parent is blocked. The code of wait is like that parent is blocked. Say suppose parent is blocked, parent will leave the CPU. Suppose, just take one case. Child will get a chance. Child will execute its case depending upon the return value. And then child will exit. And when child exits, it gives the exit status. See here, child gets a chance, child exit. And this exit status will be transferred to the wait on which parent was waiting. So child exits, child का काम खत्म, child dies, but before dying, it informs parent also. No, I'm going to die, just take care. Now when this exit status will be transferred to wait code, the wait code will return, and now parent can exit. Parent can terminate because code of parent is finished. So this way, I'm again repeating, fork, two processes, parents waits, child exits. Exit is a signal for wait. Now parent is unblocked, and now parent can terminate. So this is the sequence of fork and exit and wait. Parent will fork and wait, child will execute and exit, and done. This way fork works. Child khatam. Now parent is unblocked. Parent can execute its remaining statements if there are any. When the remaining statements are over, parent can terminate. So both are terminated gracefully. To finish, just I'm telling you whatever I've explained. To finish execution, child may call exit. This system call saves the result and provides it as an argument of exit. There are many versions of exit. You'll see in the assignment. So exit closes all open files, deallocates memory, child की memory खत्म करेगा, सब कुछ खत्म करेगा, and then we'll check if parent is alive. If parent is alive, holds the result value. Suppose after fork, parent does not get chance to execute, and child executes first. And if child executes first, child will issue the exit. But child will check whether my parent is alive or not. Yes, my parent is alive. Child will be stuck there. Child does not really die. It enters in a zombie state. अगर पेरेंट पहले चल गया, कोई दिक्कत नहीं. Parent is waiting. When child will execute exit, the status will be given to parent through Unix, obviously, through operating system, obviously, because these both are system call, and then parent can exit. But suppose parent could not get chance to execute and child executes first, child will issue exit, but holds there. Because exit तो किया, लेकिन exit को receive करने वाला wait आया नहीं अभी. where to give the exit status, that wait has not been executed. So child will remain in our Hindu mythology, we say that when a person dies, it does not just die then and there. It enters into a preta yoni, and that zombie meaning is that same pret. Fine. So it enters into a zombie state. It is dead, but is still not dead. Fine. If parent is not alive, parent exits first. Then there are variation in different operating system, but as a safe thing, child will terminate. So what is the order? Fork, parent will wait, child will exit. It's not sure whether parent or child will execute after first, which will execute first after fork. If child execute first, child issues the exit system call but enters into zombie state. यार exit तो कर दिए, but parent hasn't collected the remnant from me. And parent, if parent executes first, parent will issue the wait. Parent is waiting for child to exit. And when child exits, the remnants will be collected and then parent will exit. This is how the whole setup is there. Fine. I think we can stop here. And if there are any questions, you can ask. On the next turn, and tomorrow there will be extra class. Your uh, class representative can tell me the time.
Yes, sir. So from 9 to 11 if you're free.
Morning? No, यार. Tomorrow is
अच्छा,
holiday. सुबह मत परेशान करो.
Okay, sir. 2 to 4.
So नहीं, दोपहर में भी मत करो. 11 से 1 रखें या
Okay, sir.
आफ्टरनून यही सेम टाइम रखें 4 to 6.
Sir, as you wish.
So it would be 4 to 6 tomorrow, same time. Okay.
Okay, sir.